Okay, students, this is Mr. Shields, and let's look at some problems in Chapter 21. All right, so we're on Chapter 21, page 769, and let's look at number 1, okay? All right, so number 1 says, moving a charge from point A, where the potential is 300 volts, to point B, where the potential is 150 volts, takes 4.5 times 10 to the negative 4 joules of work. What is the value of the charge? Okay, well, so let's draw our point here. So we got point A and point B. And at point A, we have a voltage at A is 300 volts and a voltage at B that is 150 volts, okay? And it takes, to go from here to here, it takes 4.5 times 10 to the negative 4th joules of work, okay? So we want to know what the value of the charge would be. Well, if you remember you're watching the lecture videos, we see that work is equal to the change in electric potential, which is equal to the charge times the change in voltage. So then we can find the charge by doing the change in electric potential divided by the change in voltage, okay? So what is our delta V? Well, delta V is VB minus VA. And so delta V then is equal to 150 minus 300. And so delta V is equal to a negative 150 volts, okay? So let's plug everything in now. So Q is equal to the work, which was 4.5 times 10 to the negative 4th joules divided by a negative 150 volts. And so we find out that the charge, and let's just calculate this because I know we round these answers sometimes. So we got 4.5 to the negative 4th divided by 150, and that's a negative 150, and we get negative 3 times 10 to the 6th. So 3 times 10 to the negative 6th coulombs, or we would say a negative 3 microcoulombs, okay? So it'd be a negative charge, wouldn't it? Sure would. Okay, so that's number 1, real easy problem. Okay, let's look at number 9. So number 9, it says, what potential difference, let me turn to my notes. Okay. Says, what potential difference is needed to accelerate a helium ion, a charge of positive E and mass of 4 atomic mass units from rest to a speed of 1 times 10 to the 6th meters per second. Okay, so we want to take a helium ion, okay, we got a helium ion, and we want to accelerate it from initial velocity being equal to, whoops, let me rewrite that. I want to use lowercase v. So we're going to write this initial velocity is equal to 0 meters per second to a final velocity. That is final velocity, not voltage. Let me try to remember to keep it lowercase. So a final velocity of 1 times 10 to the 6th meters per second, or megameters per second, okay, or a million meters per second. All right. So we want to know what potential difference it would take to do this, okay? So to go from 0 to 1 times 10 to the 6th meters per second, okay? So we need to know, we need to find the potential difference. Well, this is a conservation of energy equation, okay? So really what we could write, if you remember from mechanics, okay, this is conservation of energy, folks, okay? It's conservation of energy. It's very easy to remember that, all right? All right, so we know that final kinetic energy plus the potential, electric potential, final potential, is equal to the kinetic energy initial plus the electric potential energy initial, right? Okay. Now, how do we define electric potential energy? Well, we just did it a minute ago. Potential electric energy is the charge times the change in voltage, okay? And you say, well, where do you get that? Okay. Oh, wait a minute. Did I do something wrong? I hope I didn't. Yeah, that's right. Charge times voltage, okay? Because you say, well, how do you get that? Well, if you remember that voltage is equal to the work done on the charge or the potential energy, electric potential energy done on the charge, okay? All right. So we know that the initial kinetic energy is 0, correct? Okay. And so then what do we have left? Well, we know that there is a final and an initial voltage. So what do we have left? Well, we know initial energy, I can't talk. We know that well, heavens, I can't even think. We know that the initial energy and the initial electrical energy and the final electric energy deals with the voltage, doesn't it? All right, so let's rearrange this equation here. And basically what we can do is we can say this right here. We can say U final, let's bring the U over, or U final minus U initial, that's electric, is equal to what? K initial minus K final, okay, and that's electric and that's initial, okay. You said, what'd you do? All right, well, I'm just moving things around here, okay. Just look, we just carried this over here, carried that over there, all right. Now remember how we define this. Well, what we can actually do here, this is the charge times the voltage final minus the charge times the voltage initial. So what we can do is we can factor this out. Okay, and so what we can do is say then the change in voltage times Q, okay, final minus initial is delta, times Q is equal to what? Ki minus Kf, right? And so then the change in voltage is equal to what? Ki minus Kf divided by Q, all right? Because we're allowed to do that. We can factor that out, all right? Now we know this one we've already said is 0. And you said, well, how did you get that? Well, look, y'all, kinetic energy is 1/2, sorry about that, 1/2 mv squared, all right? Okay. Well, if the initial velocity is 0, then kinetic energy is 0, okay? And so we have what? We have then that the change in voltage is equal to 0 minus 1/2 mv squared over what? Q. So now let's plug everything in. So the change in voltage is equal to 0 minus 1/2. Well, the mass, it tells us what the mass of the helium ion is, and by the way, it's a positive, okay? It's a positive charge, or a proton, okay? And so it's 4 positive, isn't it? Didn't it tell us that in the problem? Where are we at? Yeah. 4 atomic mass units. So it's it's a proton, positive electron or proton, so it's 1.67 to the negative 27th. Okay, so let's plug this in. So we got that times 4 times 1.67 times 10 to the negative 27th kilograms times the velocity, which was what? 1 times 10, the final velocity, by the way. 1 times, wow, boy, my handwriting. All right, let's try this again. 1 times 10 to the 6th meters per second squared divided by, and of course the charge is what? Well, it is the charge on the electron, or the charge on the proton, is 1.6 times 10 to the negative 19th coulombs, okay? And you say, why did you say a proton? Well, because, and it could be proton or electron, either one. I think your book shows you a positive electron. Well, okay. The charge on the proton and electron is the same. The only thing is the signs are different, okay? So it's 1.6 times 10 to the negative 19th coulombs. And so we should get an answer then of what? We should get an answer of negative 2.1. This is negative now. 2.1 times 10 to the 4th volts. Okay, and again, that's rounded a little bit, but 2.1 times 10 to the 4th volts is what we should get, okay? All right. Okay, you want to double check that? All right, so we got 0.5 times 4, 0.5 times 4 times 1.6 to the negative 27th, that's the mass of the proton, times 1 to the 6th squared, divided by 1.6 to the negative 19th. Okay. Did I punch something in wrong? All right, let me try that again. I got a little bit different answer. Okay. Try that again. Oh, yeah, and we forgot our negative sign right there, too. I forgot the negative. So it's 0.5 times 1.67 to the negative 27th times 1 to the 6th squared. Okay, and then divided by 1.6 to the negative 19th. Why do I keep getting the crazy? Oh, I forgot to square it. Let me pause a minute. Okay, so I was hitting the wrong button or something. All right, so we do get 2.08. Oh, I always forget to do that. So we do get a negative. Where's the negative come in? Right there. Negative 2.08 times 10 to the 4th volts, or 2.1. Okay? All right. Okay. All right, let's look at another problem. Let's look at number 16. Okay? Number 16. Okay, so number 16. Oh, says what? Says we have a 2 by 2 centimeter by 2 centimeter parallel plate capacitor. So let's just draw it, and I'm going to draw it like this. So there's one plate, and there's another plate, and they're symmetrical, just pretend. And it has a 2 millimeter spacing. So the space between here, from here to here, is 2 millimeters. Okay, so that's going to be equal to the distance. Okay, all right, or x, however you want to write it. Okay, that's the distance between the plates. And it has a 2 millimeter spacing, and by the way, that's 2 millimeters, which is equal to 2 times 10 to the negative third meters. Okay. All right, and the electric field strength inside the capacitor is 1 times 10 to the 5th volts per meter, okay, or newtons per coulomb, however you want to write it. So the electric field strength within the capacitor is 1 times 10 to the 5th volts per meter, or newtons per coulomb, okay? And those are equivalent units, okay? A newton per coulomb and a volt per meter, they are equal, okay? Believe it or not. All right? Okay. What is the potential difference across the capacitor A, and how much charge is on each plate? All right, so A, we want to know how much potential, what is the potential difference across the capacitor. So we want to know delta V. And then B, we want to know the charge, don't we? Q, all right? Okay. All right, well, if you remember from our lecture and from, if you watched our lecture videos, we know that we can find the electric field on a capacitor using the change in voltage of the capacitor divided by the distance between the plates, okay? So therefore, rewrite the equation. We say the change in voltage then is equal to what? The electric field through the capacitor times the distance, okay? And you say, well, where does that come from? Well, if you do if you were to take my Cal-based physics class here at Snead, we do this experiment in lab where we take a parallel plate configuration and we actually look at the change in voltage as you move away from the source, as you move from the positive towards a negative plate. And you can see how that the voltage decreases as you move down the electric field. And so that's where this equation comes from, okay? All right, because that's why as you move down an extension cord, the farther you get out on an extension cord or even an electrical power line, okay, the farther down that line you get from the source, the more the voltage drops off, okay? That's why we have to have substations ever so often, ever so many miles, okay? You can't just put voltage in a wire and just shoot it out, 100 miles and expect the same voltage to come out on the other end, because it just doesn't work that way, because that current is flowing through wire which has resistance, okay? Now, okay, so we can find then the change in voltage. So the change in voltage, the potential difference, okay, and that's what we mean when we say the change in voltage is the potential difference, is equal to what? Well, let's see. We got the electric field, which is 1 times 10 to the 5th volts per meter, times what? That's 2 times 10 to the negative 3rd meters. And so let's do that calculation real quick. And what do we get? We get 1 to the 5th times 2 to the negative 3rd. And what do we get? We get, oh, I didn't do that right, did I? Let me try it again. All right, we get 1 to the 5th times 2 to the negative 3rd. And we get 200 volts, okay? Well, I'm not punching the right buttons on my calculator today. Whew, it's Friday. I guess I'm too anxious about quitting. All right. 200 volts, all right, so that's the potential difference or the change in voltage, okay, across the plates, all right, based on that spacing, all right. Now, if the spacing changes, that would change, okay. You can see that the voltage is related, the change in voltage is related to the distance between the plates, okay. Now, all right, then part B says what? It says how much charge is on each plate, okay. Well, we can find that using our capacitance equation. We can use this equation right here where we say that the electric field, I think this is equation 20.7, 20.7, that the electric field is equal to the total charge divided by what? Epsilon naught times the area of the plates, okay? So we can find then the charge is equal to the electric field and the capacitor times what? Epsilon naught times the area. Okay, so epsilon naught times the area of the plate. So let's plug that in now. So the charge is equal to what? Well, the electric field was 1 times 10 to the 5th volts per meter times what? Times epsilon naught. You need to memorize that. Put that on your formula card now for your midterm and final exams, okay? 8.85 times 10 to the negative 12th, and that's coulombs squared per Newton meter squared, times the area. And the plates were what? The plates, and I forgot to write this down a minute ago, and I apologize. The plates are, heavens. What was the size of the plates again? 2 centimeters by 2 centimeters. So the plates are 2 centimeters by 2 centimeters, which is what? Well, that's actually 0.02 meters by 0.02 meters, right? So let's plug that in. So we got 0.02 meters times what? 0.02 meters. And let's do the math on that. And what do we get? Well, we get 1 to the 5th times 8.85 times 10 to the negative 12th times 0.02 times 0.02, and I put that in parentheses. And we should get, there I am getting crazy answers again. Oh, I'm sorry. I was looking at another problem. Oops. Okay. Looking at my answer sheet in the wrong place. You ever do that? Okay. So we get 3.5 times 10 to the negative 10th. Actually, it's 3.54 times 10 to the negative 10th coulombs, okay? Now, what would that be in nanocoulombs? Well, that would be what? That would be 0.35, or if we went to what? What's 10 to the negative 12? We could say 354 picocoulombs, couldn't we? Yeah, because pica is 10 to the negative 12. Okay, so we could say 0.354 nanocoulombs or 354 picocoulombs. All right, either way, or you can write it that way, okay? You need to learn those prefixes, okay? Okay. All right, some of you are probably wondering about that volt per meter. How is a volt per meter and a Newton per coulomb equal? Okay. All right, well, let's look at this real quick. We got a volt per meter. How in the world is that the same unit as newtons per coulomb? Well, what is a volt? A volt, 1 volt, y'all, 1 volt is what? The number of joules per coulomb, right? Per meter. And I'm going to do it this way, meter over 1. Because what is a volt? A volt is the work done on the charge, and the unit for work is joules. Well, what is a joule? Well, a joule is a Newton meter. So we got a Newton times a meter divided by a coulomb divided by meter over 1. All right, now if you remember anything about complex fractions, you can take the bottom, flip it around, and multiply it by the top. So you can come in and say then this. You can come in and say a Newton meter per coulomb times, flip it over, 1 over meter. See, take the bottom here and flip it and multiply it. So these cancel out and you are equal to a Newton per coulomb. So a volt per meter is actually the same unit as a Newton per coulomb. It's the same value, all right? Okay. All right, so let's do another problem here. I think we got 1 or 2 more maybe. Yeah, looks like we got 2 more. Okay, I'm going to do 5 this chapter. So number 37. And that's on page, those were on page 769. This is on page 771, top of page 771, okay? All right, so what are we doing, number 37? All right, so number 37 is a good capacitor problem. We said we got 2 centimeter by 2 centimeter square aluminum electrodes. So here again, let's just draw them. Okay. So these are 2 centimeters by 2, and it's actually 2.0. Get our sig figs right. Okay. All right. That's centimeters. Or we could say it what? 0.02 meters by what? 0.02 meters, right? Okay. All right. That's the dimensions of the aluminum plates. All right. Now, and they are spaced, how far apart are they? They are spaced 0.5 millimeters. So the distance is equal to that, which is the same as saying what? 0.5 times 10 to the negative what? Third meters. Or you could say 5 times 10 to the negative fourth meters. You could say it that way too, all right? Okay. Either way, it doesn't matter now because it's right, all right? Okay, and we want to know, and by the way, and it's connected to a 100-volt battery. So we got a battery up here. We got a battery, okay, and positive and negative. And so it's connected to these plates. Of course, you got negative, you positive, and you got negative, okay. All right, so it's connected to a 100-volt battery. So the voltage on the battery, I'm going to write it right here, the voltage is 100 volts, okay? All right. Okay. So part A wants to know, A, what is the capacitance, and B, what is the charge on the positive electrode. So B, we want to know what is the Q positive, right? We want to know Q positive, don't we, on the positive electrode, all right? Okay, so let's just work through this now. So we know that we can find from our capacitance equations, I think we're looking at equations 21.18 and 21.20. Okay, we know that capacitance, this is going to be part A, capacitance is equal to what? Well, since we're not just looking at general capacitance in general, we're looking at actually the dimensions of the capacitor, then we have to use this equation, okay? If we were just looking at capacitance in general, then we could say what the number of coulombs per volt, and we could do it that way, couldn't we? Okay, but that's not what we're doing. Okay, we were actually given the dimensions, so here we have to. This is a little bit more. I guess you could say a little bit more precise equation, whereas a general capacitance equation, it works too if we don't have the dimensions, but this is more precise. All right, now, so we know then that the capacitance epsilon naught is what, 8.85. I'll tell you what, I'm going to have to move because I'm not going to have room to write. Let me come over here. We got A, so we got what? Capacitance is equal to, epsilon naught is 8.85. Now, folks, you need to make sure that's on your formula card. Times 10 to the negative 12th, and those units are coulombs squared per Newton meters squared, okay, times what? The area, which is 0.02 meters, times what? 0.02 meters, okay, and then divided by the distance, which is what? Let's just use this one. Let's say 5 times 10 to the negative 4th, or you could say 0.5 times 10 to the negative 3rd, either one, okay, meters, okay. All right, let's do the calculations. Let's see what we get, okay? So we get what? So we got 8.85 to the negative 12th times, all right, I'm going to put this in parentheses, 0.02 times 0.02, close parentheses, divided by 5 to the negative 4th. And what do we get? We get 7.08 times 10 to the negative 12th farads, and you say, how do you know it's farads? Because it's the coulombs per volt. Coulombs per volt. Coulombs per volt is a farad, okay? Now we can round this up and say 7.1 times 10 to the negative 12th farads, or we could say 7.1 picofarads, and let's use our prefixes, okay? Picofarads, all right? Okay, and you say, well, why would you round that up? Well, look at your significant figures. This is there's actually 2 here, and there's 2 there, so 2 sig figs, all right? Now, okay. All right, now what about part B? All right, well, let's go to, this was what, 37B? Yeah, 37B. 37B says, what is the charge on the positive electrode? So now we're just looking for charge. Well, here we can use this equation right here. It's just a general capacitance equation, which capacitance is equal to the total charge divided by the change in voltage. Okay, so to find the charge then, we just do what? The charge is the capacitance times the change in voltage. All right, so charge then is equal to the capacitance, which was what? 7.1 picofarads. Okay, 7.1 picofarads. Please stop doing that, pen. My fingers are so big. And the voltage was what? It was 100 volts, wasn't it? Yeah, whoops, it was 100 volts. So it was 100 volts, okay? And so then the charge on the positive plate is what? All right, well, let's just do the math. So we got 7.1 to the negative 12th times 100, and we get 7.1 to the negative 10th, 7.1 times 10 to the negative 10th coulombs, or we could say a couple of different ways, 0.71 nanocoulombs, or we could say 710 picocoulombs. We could say it, move the decimal 2 more places to the right and say 710. So we could say it either way, okay? All right. And so, and you say, you say, well, why would we do that? Why would it just be, and of course that's positive, by the way. That's positive, okay? Positive, because remember, y'all, you got to have the same amount of charge on each plate, okay? Same amount of positive and negative, okay? All right, that's number 37, so I hope that helps. And then the last one, I think, is number 53. And this is on page 771, yeah. All right, y'all, I got to stand up a minute. Sitting on this old hard stool gets old. All right, now. All right, so let's look now at number 73. This is good potential energy, potential electrical energy of a capacitor. It says, to what potential should you charge a 1 microfarad capacitor to store 1 joule of energy? So we got a capacitor here, and let's just say it's a You know, capacitors have this right here on top of them. Well, they are, or a couple of connections. Okay, let's just do it this way. All right. You got to have, all right, and there's your capacitor. Okay. All right, now, and of course that's in a cylinder. That's a cylindrical capacitor, like in a old lawnmower, you know, the little condenser. If you tear out the points in condenser in these old lawnmowers, old cars, old tractors, that condenser is a capacitor, okay? All right, so it tells us then what? That we want to know what potential, so we want to know the voltage, question mark, would you need to charge a 1 microfarad. So the capacitance of this capacitor is 1 microfarad, that's 10 to the negative 6, to store electric potential energy of 1 joule, okay? All right. Well, we got two or three different equations that we can use to find that deal with the electric potential energy of a capacitor. And so if we look at equation 21.22, we see that the electric potential energy of a capacitor is equal to 1/2 times the capacitance times the change in voltage squared. Can everybody see that? Let me write it again. Electric potential energy of a capacitor is equal to 1/2 the capacitance times the change in the potential difference, or the change in voltage, squared, okay? So let's solve for what? It's wanting to know what? What is the potential? To what potential? Potential, didn't say potential energy, it says potential. That's electric potential. That's how much voltage, okay? Please learn the terminology, okay? Potential energy is joules. Potential is voltage, okay? All right. So we want to know V, don't we? All right, well, we have to do a little bit of mathematics here, so we're going to do what? We're going to multiply both sides by 2, okay? And we're going to do this. I'm going to work it in steps here. So we're going to say multiply both sides by 2. And we get what? 2 times the potential energy of a capacitor is equal to C times what? Delta V squared. And then we're going to divide by the capacitance. Okay. And so we come down here and we say 2UC divided by what? The capacitance is equal to the change in voltage squared. And now we're going to take square root of both sides. Okay. Take the square root of both sides, and we're going to come up with this equation. We're going to come up with delta V of the capacitor is equal to the square root of 2 times the electric potential energy of the capacitor divided by the capacitance. So let's plug everything in, okay? Now you say, Ms. Shields, why do you do that? Because that's the physics part of this, okay? You say, well, that's math. Well, that's true. It is math, but it's the physics. You got to understand the physics to be able to solve these equations, okay? You say, well, why do you do that? Because you need to solve for the equation first and then plug in all your quantitative values and then use your calculator, okay? Because then it's just simple mathematics. So as Dr. Zitelli would say, the physics is over with, now let's do the math, okay? So we say 2 times the electric potential, which was 1 joule, right, divided by the capacitance was 1 microfarad, all right, 10 to the negative 6. So what is my change in voltage? All right, so let's do this, and we should get around 1400 volts, so let's see if we do. So we got 2 times 1, of course, is 2. So 2 divided by 1 to the negative 6th, and then take the square root of that number. And we get 14.2 volts, okay? Now you say, how would we do that? Well, if you go back and look at the values in the problem, you actually had 2 significant figures, so you could just say 1400, okay? So if you want to come in here and say this right here, 1400 volts, that would be accurate too, okay? All right. And you say, man, that's a lot of voltage. That particular voltage is common for capacitors, okay? So that's not too high, okay? All right, I hope this helps.